I have written here, I guess first order, second order, but there's something called zeroth order, and I give a third order as an extra practice for. And you can looking at this whole reaction is under consideration of concentration of A, which is a reactant, is making a product. So this is a very simplified case, but this is a case that where we're going to, I guess, build up some understanding. And so they wanted to essentially give an understanding about how to write a rate equation and recap on the unit on the KR, and this is a rate constant is KR, and what is called the half-life. The half-life is something that is people trying to keep track of how long does it take for this concentration. And we are going to something called initial concentration. At time t, concentration of A is same as A naught. This is the same for everyone. So this is a initial concentration, we call IC. So let's do the rate law, the first order. And I will do this practice for now, but the next one I'm going to do it in a different way. So rate here is minus dt dA, because A is a consuming substance, and so that's a reactant. I need a negative sign, and the rate, which is supposed to be a positive one, will go KR, and to the power of concentration to the 0, right? Which means nothing. This is just a 1, right? So which is just a common constant. And now normally what people now transform this one is, let me just say I want to care about concentration of A change, the rate of concentration of A change, which is a minus because it is a decreasing concentration as function of time, and this is becoming 10. Okay? So that's the zeroth order. Okay? What about the first order? Change in the A dt is, I know this is a decreasing, so I'm put on the minus sign there, and KR to the power of 1, first order. In the second order, we can do the same drill now. KR to the second power, third power, any power now, we start to have a sense of this. Let's do the third power. So I can finish up writing this equation that way. So here I quickly made a transition from rate being plus KR times concentration function to the, just this one itself is a negative numbers of the rate. So this one is actually the rate. But I'm kind of combine this one into this. So I have this equation now in my hands. And once again, my initial condition is A is A naught at time is 0. So I can do that. So what do? This one, you always do the separation of variables. So dA is minus KR dt. Okay, so here too, dA over A minus KR dt. So that's here, dA A squared minus KR dt. So we are in a place to do this, tackle this problem now, and all I need to do is do the integration. So I will just say, let's do the integration. do the integration. Is actually, this is a constant, I can do it here. Do the integration. Do the integration. So far, so good, right? And then I can actually even complete this one by saying that, okay, the time is changing from 0 to t. All right? What is my concentration? This equation says that you want to put the quantity shown as a concentration A. At time 0, this is a naught. And at time t, that's an A that you're looking for. So this equation is A minus A naught is minus KR times T. Okay. So that's an equation that you got. So therefore, your final answer is, this is an answer that you're looking for. What is the time dependence of concentration of A? Minus T. So that's the one. Okay, solve that. So what about here? Same thing. You start from 0 concentration to concentration at T. Time is changing 0 to T. Same here. T. So this is the same parallel, and this one is a little handled differently because remember what's this? Dx over x integration. That's ln x, right? So this one is essentially natural log. We have seen this form a lot, and so that's a divided by a naught. The difference in natural log form, which is a ratio of these two concentrations, is minus KRT. Probably this is the most famous equation that because when you have this one, people write this one as A is an A naught e to the minus K R T. And this one has we call exponential decay. So if you look at the A, for time, start from A now, and it decreases like this, and it decreases rapidly. If K value is really fast, like this, K value is slow, you like this. But it is an exponential decay function that can be shown up here. This one is easy, right? This one is just like this, linear function. It's a linear function, whereas that one is a decay function. So the one that I put in a box is the one that represents this. Okay. So 0th order, yeah, I can do that. 1st order, I can do this. What about 2nd order? This one is more like 1 over x squared integration. I'm pretty sure you have done this calculus in your high school. Probably has never seen that I've never used that ever since. Now it's came back and it's useful now. This one is, you remember? Like this is like this is x to the minus 2. So that was like a minus 1 over x plus c, right? This one is this, right? So you do that. So here, minus. And then I'll put something like 1 over x. And this is my notation, and textbook use the same notation. This line means the differences. A, starting from A naught to A. So this is the differences using this term. So having written that, it's just minus parenthesis 1 over A minus 1 over A naught. That's it, okay? So that's what this in my notation. So I just written down, and that's the difference up and down. The left hand side is always easy. Okay, left hand side is always minus KRT. And happily I can get rid of this plus and plus. So therefore, this is your final equation, which is 1 over concentration minus 1 over concentration naught is KRT. This one has you can have a little bit more. Where's my note? Forgot I put my note there. Here. I didn't even pick it up anything. Okay, because it is kind of involved, and I like this form as it is, but if you actually work it out, you can get the form that you look familiar with, which is I want the equation as an A is something, right? And the answer for that can be found, and that is A naught 1 plus KR P. So that's an equation that you can find out. But I like this form because it's kind of much nicer, easy to understand. So that's here, right? If you look at that, if you do the integration, this is nothing but 1 over x cubed dx integration, right? So therefore, it is minus 1 over 2, and then the a squared. So this is pretty much the minus 1 over 2, 1 over x squared, if you do the integration of that. And the difference is here, top is a, bottom is a naught. So therefore, this is a minus 1 over 2, 1 over a, to the cube, minus a naught. So this is just the difference in the 1 over square, and that's minus KR cubed. And this one is luckily always cancel out. Therefore, that's an equation. If you want a much more neater writing, you can write a square minus a naught square is 2 times KR. So that's the proper equation form. So it's just a matter for you to get used to solve this one. And let's check on the actual rate law constant itself. Okay. This one, this KR, because it's a zeroth law, not depending on here. So this unit of KR is just nothing but, let's say big M, mole per liter, divided by second. Right? That's their unit. What about here? This one? The answer is right here, right? The answer is essentially m over second. That's always the rate. And then this is m. Right? So therefore this one is 1 over second. Okay? So that's the unit for this. So the KR has a unit of 1 over second. Does it make sense? So when you have a first order equation, this is how this thing defined, and the rate law has a unit of 1 over second. Okay? And when it's a second law, once again, the left hand side is always m over second, right? Molar concentration divided by second. This is a m squared on your right hand side. So what's this one to compensate? I need a 1 over second goes down, and I need a 1 over m, even needed one. So this one is essentially their unit is 1/2, 1/molar concentration. You can figure out the rest of it. So these are the 3 pointing items. You need to know how to write the rate law equation. If somebody give you a first law, second law, you just write it down. And initial concentration is A naught, and then understanding the KR unit. The last thing is a half-life, and this is just a final punchline of what you need to do. And it's pretty easy. What you need to do is you plug that in the value of 1/2 of original concentration, and then this one is at the value of 1/2 half-life. Right? If you do that, you see the numbers now already? It is a 2 times. Okay. So here, the 0th order, the half-life. Okay, so this one goes down into 1.5. Negatives, let me cancel it out. Is A squared, yeah. A naught divided by 2. That is the half-life, which is by increasing the initial concentration, your half-life is linearly increasing. This is the one way to how the half-life is sometimes an easy quantity that you're trying to find out, and then the half-life is and the initial rate concentration. This is how they are dependent. What about here? This one is essentially you're putting in A naught to the half is A naught e to the minus k RT. So I can use this or I can use that, which means this bond becomes 1.5, and the whole thing it becomes minus ln2 is minus k RT